Welcome to Ready to Derive. In this video, we begin by distinguishing between absolute and relative max and min, collectively known as Extrema. We then add a third existence theorem to our toolkit. We have been introduced to the Intermediate Value Theorem, the Mean Value Theorem, and now we get to explore the Extreme Value Theorem. Finally, we learn how to find the location of absolute extrema using the candidates test, otherwise known as the closed interval method. So, without further ado, let's get started. So let's begin by establishing some vocabulary. Here we have a picture of the Himalayas, and as we all know, the highest mountain in the world is Mount Everest at 8,848 meters. And being the highest mountain in the world, we have a special term for that. We say in math speak that Everest is the absolute or global maximum. Absolute maximum, the highest mountain in the world, and global makes sense when we're talking about the world as well. So, but this also applies to functions. And nearby Lhotse at 8,516 meters, that's no trifle. That's a pretty tall mountain in itself. But because it's not the highest mountain in the world, we give a slightly different terminology. We say that Lhotse is a relative or a local maximum. And what relative means, well, relative to Mount Everest, it's not the highest, but it's still a maximum. And local suggests that in that vicinity, so if you were kind of, circling around the base of Lhotse, it is going to be the highest peak in that neighborhood or in that vicinity, and that's what we mean by a local max. So we're going to take a look at the mathematical definitions of extrema, absolute versus relative max and mins. And it all begins by ensuring that C is a number in the domain of F, so that f of C is defined. And if we would like to know if f of C is a maximum, so let's just draw a picture of that. So any sort of maximum is going to look something like that. And f of C is the y value that corresponds to that particular x value. So if the function was kind of continuing down like this forever, and that f of C value was greater than or equal to the value of the function for all x's in f's domain. So if that truly was the greatest value of y, we would say then that it occurs, that happens to be an absolute max. Now, what's the alternative? Well, so what would make a relative max? Well, if fc is greater than or equal to f of x, still conditioned to be a max, only when x is near c. So imagine if this function, instead of continuing down, came up and achieved an even higher value, a higher y value, then that particular value of c, at that value of c, we would say that f of c is a relative max. Similarly, if we want to look at what it means to be a minimum, so here's a minimum at, say, the value c, and the minimum value that function achieves right there would be given by f of c. In this case, we would want the reverse to be true. We would want f of c, that value of y, to be less than or equal to other values of y, and if that was true in the whole of f's domain, that would become an absolute minimum. And not surprisingly, keeping that same condition true, but only when x is near c, that would ensure that it's relative minimum. So again, if the function turned around like this and came back up, in that case we would say f of c is a relative min. So why do we care about extrema of functions? Well, it helps us to answer problems like the following. What are the optimal dimensions of a can that will maximize its volume given a fixed surface area? So you have a fixed amount of metal you can use, and you want to optimize the volume given that fixed amount of metal. What is the greatest height reached by a projectile? What is the minimum distance from the origin of a point traveling on a particular curve? And what dimensions will produce the least waste when making a cardboard box to hold a specified volume? So all these applications are looking for, as you can see, greatest, maximum, minimum. They're looking for the value of extrema functions, and this sort of branch of calculus is called optimization, and we will look at this in more detail in a later video. So let's practice finding absolute and relative max and mins on a closed interval, which is what we'll be doing when we get to optimization problems. They'll often be closed intervals. So over the interval 0 to 8. So let's have a look. We need the absolute minimum to start with. So it seems like the lowest y value that we achieve is 0. There's no other y value on this function lower than that. So you could say that the absolute minimum value of the function is 0, and this occurs at x equals 5. But a more efficient way to say this is that the absolute minimum is f of 5, as we did before, f of c, which equals 0. That kind of encapsulates everything you need to know. Now, the absolute max, let's look up here. It doesn't seem to get any higher than 6. Well, no, it can be 6 because f is not defined at x equals 0. Maybe 5.99? Well, not really, because I could give you a higher value of y, like 5.999. So there is actually no absolute max, of this function because it's not defined at x equals 0. Now, what about relative min? So technically, the absolute min is also a relative min, but it's a little redundant, but we could, acknowledge that true. It is, in that vicinity, it's also a relative min. But here's one that might have taken you by surprise. We have actually a relative min at 2 because, well, f of 2 equals 1, and 1 in the vicinity around here, so in this vicinity, around x equals 2, the value y equals 1 is smaller than all the other values. So the other values on either side are here, and f of 2 equals 1 is relatively a minimum value. Now you might say, well, what about then at x equals 8? But the problem with x equals 8 is we don't know what's happening to the other side, on the other side of the function. So relative mins and max can only occur, they can't occur at endpoints, whereas absolute mins and maxes can. And so finally, a relative max. We have 1 here. So f of 3 equals 4. That's one relative max, and it looks like we have one here as well. So at f of 7, we have a relative maximum value of 2 in that vicinity. So in the previous practice problem, we saw that the function had an absolute min, but not an absolute max. And the problem was that discontinuity, it seemed, at x equals 0. So here's a challenge. Can you draw a continuous function on a closed interval, say 1 to 4, that has no absolute max or min? You could pause the video and try out a few iterations and see if you could make this possible. And I'm going to show you what my students, sort of 3 diagrams that my students tend to come up with. Maybe 2 initially, they feel like it disproves this. But if we look a little deeper, so look at this. It's easy to think that because there's no like curvy bits, there's no critical values, that there's no absolute max or min. But it turns out that whatever this y value is lower than any other y value on the function over that interval. So we say that is the absolute min. And similarly, for x equals 4, whatever that y value would be the absolute max. So that seems to hold true. That continuous function does have an absolute max and min. Let's look at this. This is another diagram that's often presented. But once again, there is an absolute minimum value of y. It just occurs at a couple of different x values, and that's okay. It's okay for the absolute, for that particular absolute minimum value to achieve a couple of times. Similarly, there's no problem that the absolute max is achieved at different locations over the interval. And finally, this is a common diagram because it feels like this doesn't have an absolute max or min, and it doesn't have 1 or even 2 or 3 absolute max or mins. It actually has a lot. So it turns out that whatever this y value is the absolute max over that interval of the function and the absolute min over that interval. And it's all to do with, it's because of this definition. So for an absolute max, for the whole domain, that has to be true. So the equal sign, because in fact, f of c is equal to f of x all across the domain, and ditto, f of c is less than or equal to f of x, both cases they're equal, we say that whatever that y value is the absolute max and the absolute min of that function over that interval. The exploration in the previous slide brings us to the third existence theorem we introduced to in calculus, known as the Extreme Value Theorem, the EVT. So it says that if f is continuous, if a function is continuous on the interval a, b, so let's do that here. Here's a function that's continuous on a, b. We'll make that a and that value b. So if it's continuous over that interval, then it must follow that f attains an absolute maximum value, f of c. So let's have a look here. It looks like that must be where c is located, and that y value is the absolute max, and an absolute minimum value, f of d. So it looks like that would occur right here, and that's would be f of d here. And that must occur for some numbers c and d in the interval a, b. Notice that it's in the closed interval a, b, and not the open. So c and d don't have to be strictly between a and b, as we saw in the previous slide. It could also occur at the endpoints a and b. So let's just sort of formulate where exactly absolute extrema can occur in a closed interval. So we saw in, for example, in a closed interval, so we saw it with this function, the absolute extrema actually occur at the endpoints. We could also envision, let's have something like this. Now remember, the function just has to be continuous, so it could look something like this. In that case, the absolute min occurs at an endpoint, but the absolute max occurs at what we formally know as critical value. So be prepared for that. And then the last possibility is one that we expected, or we've seen before, something like that, where the absolute max and min, notice that they occur. So in this case, let's have a look at this. In this case, it's where here we know f prime c equals 0, and that's also true here. Here, f prime is undefined, but it can't really occur anywhere else. And because you might say, well, why couldn't we have, how do we know that there is not, it doesn't even get higher than that? So you might say, well, how do we know it doesn't go like this and then maybe get a bit lower before it goes here and up? And then, but the answer is that, well, if it did do a turn like that, then you would have introduced another critical value. So if we know all the critical values, we will cover all the possibilities for absolute extrema on the interval. So that brings us to this conclusion that absolute extrema can only occur at the endpoints of the interval or at the critical values of f of x over that interval. And now we'll formalize that in a test that helps us to establish the location of absolute extrema. So now we're going to look at what's called the candidates test, also sometimes referred to as the closed interval method, to find the absolute extrema of a function on a closed interval. And step one is to find the critical values of f of x. Let's call these C1, C2, C3, as many critical values as you find in the interval a, b. Why do we find these critical values? Because we know they are candidates for the location of absolute extrema. Step two is to find the values of the function at the endpoints and the critical values. And often it's nice to organize it by completing a table that looks like this. So A, C1, C2, C3, and B are the only candidates, as we discovered in the last slide, for absolute extrema. So you would take your value, your endpoint A, and you'd plug it into the function, repeat for all of these. So you're just evaluating the function at all of these candidate values of x. And not surprisingly, the largest of these values would be the absolute max of the function over that interval, and the smallest will be the absolute min. And it's possible that you might, a couple of those values in the table will form the absolute min or max. Notice that what we don't have to do is establish whether C1, for example, is a relative max or min first. That would be kind of a waste of time. So we could do a number line analysis. Say for C1, say we found that f prime changed from positive to negative there. Then we could say, okay, at C1 we have a relative max, but that doesn't help us to determine whether it's also an absolute max. It would be an additional work to do. We'd basically have to just do what's in the table. So we can bypass this and just go straight to the table, straight to this candidate's test for establishing the values of the absolute max and min of a function. So let's practice using the candidate's test by finding the absolute max and min values of this function on the interval -2, 3. So the first step is to find the critical values. So let's take the derivative, which is 3x squared minus 6x. That can never be undefined, so let's just set that equal to 0 and solve. 3x, x minus 2 equals 0, we factor that. And that gives us that x equals 0 and 2 are the critical values. Step 2 is to set up the table. So in the table, notice we put the endpoints, -2 and 3, and then we go and insert the critical values there. And then we just plug these x values into the function, this function up here. So that would be, it comes out to be -16. This comes out to be 4, 0, and 4. And once we have that table, step 3 is to conclude. So in terms of the absolute max, it's clear that the absolute max is, let's see, it seems to be 4, and it achieves it twice. So the absolute maximum value it attains is 4. But again, you could write that as your answer, but also it's helpful if you write it in this way, you're establishing where that occurs. So at both 0 and 3. And then for the absolute min, we see that the lowest it gets to is 0. But once again, oh, not 0. My apologies, take that back. The lowest it gets to is -16. So the absolute min technically is -16, but when we write it like this, it tells us the x value at which it occurs. Let's do one last practice problem using the candidate's test to find the absolute extrema of this function on the interval 0 to pi. So step 1 is to find the critical values. So let's take the derivative of this, will be 1 minus 2 cosine x. The derivative will never be undefined, but it's possible it could equal 0 whenever cosine x equals 1/2. And to solve this problem, let's think about where this could be. So we know that the cosine of pi over 3 is 1/2. And we know that we're only interested in the interval 0 to pi. So there is no value, there's no point considering what angle in there would work because cosine is negative in that quadrant. So that leaves us with just one critical value. So step 2 is to create the table. So here are the endpoints 0 and pi with that one critical value. And then we just plug in. So remember, we're looking at the function itself. So f of 0 will be 0 minus 2 sine 0, which is just 0. For pi over 3, we get pi over 3 minus 2 sine pi over 3. And that's pi over 3 minus 2. So sine pi over 3 is rad 3 over 2. Those 2's would cancel out. But at some point, it might be good just to grab a calculator, and that comes out to be -0.685. And finally, pi minus 2 sine pi comes out to be just pi, sine of pi being 0. So then we get to make our conclusions that the absolute max would occur at f of pi, which equals pi, which is, just to give us a number, is approximately 3.14, and the absolute min occurs at pi over 3, And if we want to give the exact value of that, it would be pi over 3 minus rad 3. And that brings us to the end of this lesson. I hope you found it helpful. And if you did, please do click like and/or subscribe to my YouTube channel, Ready to Derive. Thank you.